On August 21, 1945, physicist Harry Daghlian conducted an experiment at Los Alamos to measure neutron reflection using tungsten carbide blocks around a plutonium-239 core. As he stacked the blocks, neutron levels rose dangerously. While placing the final block, it slipped and fell directly onto the core, triggering a sudden chain reaction. A burst of Cherenkov radiation lit up the room. Daghlian received a fatal dose of radiation and died 25 days later, becoming the first person to die in a nuclear accident. The plutonium core used in the experiment was intended as the third atomic bomb during World War II, had Japan not surrendered. Fortunately, it was never deployed. This core would later be known as the Demon Core. To trigger a nuclear explosion, 3 key conditions must be met: sufficient critical mass, the presence of neutron reflectors, and proper compression or density. Materials such as beryllium and pure carbon are excellent neutron reflectors due to their low neutron absorption cross-sections. Boron, gadolinium, and cadmium, on the other hand, strongly absorb neutrons and are used in reactors to control reactions. Plutonium-239 and uranium-235 both absorb neutrons moderately, enabling them to sustain chain reactions. The critical mass of plutonium-239 is about 10 kilograms in a bare sphere, but with reflectors like beryllium, only 6.2 kilograms is sufficient to reach criticality. On May 21, 1946, nearly a year after Daghlian's death, physicist Louis Slotin conducted a similar test with the same plutonium core. Using a screwdriver, he manually kept 2 hemispheres of beryllium apart. The tool slipped, closing the shell completely and causing the core to go supercritical once again. A flash of radiation burst through the room. Slotin knocked the reflector away, but the exposure was fatal. He died 9 days later. 8 others present were also exposed to varying levels of radiation. These 2 incidents prompted the U.S. to ban all manual criticality experiments. Future tests were required to be conducted remotely. The Demon Core, having experienced 2 supercritical accidents, became increasingly radioactive due to rising levels of plutonium-240, which undergoes spontaneous fission more frequently. Its final fate is uncertain. Some reports say it was recycled, others say it was scrapped. Plutonium-239 undergoes spontaneous fission at a low but constant rate. 1 kilogram generates roughly 50 neutrons per second. With 6.2 kilograms, the core produced over 600 neutrons per second. Surrounded by reflective material, these neutrons were bounced back into the core, dramatically increasing the reaction rate. Each accident resulted in lethal doses of neutron radiation, gamma rays, and radioactive particle emissions. Cherenkov radiation, the distinctive blue glow, appeared as fast-moving electrons exceeded the speed of light in air or water, disrupting local electric fields and releasing visible light. The Demon Core stands as a haunting reminder of the dangers of nuclear experimentation. 2 brilliant scientists lost their lives, and countless others were affected, not by weapons of war, but by curiosity, miscalculation, and a fraction of a second.